Okay, so here we have some examples for class 17, and this is an example out of Munson's book, and we have some type of movie theater, outside movie theater, with the dimensions of 70 feet by 20 feet, and of course, apparently we're watching this little horse and buggy thing. So just to give you sort of an idea of what we're looking at in 3 dimensions, maybe here. Yeah. And we have the wind coming out in that direction out of the thing. And the wind's blowing at 50 miles per hour. And this is 20 feet by 70 feet. And what we want to do is we want to estimate the wind force on the screen. So really the amount of drag that's being taken place. So let's convert this to feet per second. So that's going to be times 5,200 divided by 3,600. So we get 75.33 feet per second. We're going to take a density, since we're using feet per second, we'll use slugs per cubic foot. And the density of air, we can take it at 2.38 e to the minus 3 slugs per cubic foot. And we could look up for what a flat plate is going to be, what we would use for a flat plate. Generally speaking, there wasn't a specific one, but we had this right here where we have a flat subjected to the drag of a flat plate normal to the flow. So that was the one that we decided to use for this particular example. So we're going to say that we're going to have a drag coefficient of 1.9. And so we'll find what the drag is going to be equal to is the drag coefficient times the dynamic pressure times the area. So we end up with 1.9, 1/2, and then 2.38 e minus 3 times our 75.33 squared, and then times the area, which is 70 times 20. So what we're going to be left with is about drag force of 17,020 pounds right here. That's a heck of a lot. You might just think about what we would have to do to like design the legs on these things, right? We would kind of like take a look at it, do a free body. Maybe here I'll draw the legs behind the thing. We draw a free body diagram of the thing where it was, we're cutting off right there. So we'll remove the ground. And of course we have the weight of the piece, but we have a force that's really acting kind of on the center of pressure, which will be in the middle of this right here. So we'll have the drag force right there. So we'll have a force that's operating as the reaction force in the x direction. We'd have a reaction force in the y direction because of the weight, but we'd also have a moment that's being placed on here. And because this one's going clockwise around here, this one would have to go counterclockwise, so you would have a moment. And you'd want to design this for the stress, and so the stress would be equal to mc over I. But most of the time when we are doing this type of thing, we would try to probably pick out a cross section from a table. So we often will go m over the section modulus, which is a combination of c and this, and we would set that equal to, and by the way, there would be 2 of these, so you had to be kind of careful that we actually would want to have maybe multiply this by 2 to be able to get find out what the minimum section modulus would have to be of each of those shapes. And we would want to divide maybe the yield strength by a safety factor, right? So we could find out what our z would need to be by working through that. Anyway, and the z we could get like maybe in the back of Shigley we could find for a particular shape. Maybe we would pick, and probably not a very good candidate, but we would like maybe get a channel, right? Maybe we would want a channel, and we'd probably want to use it about the 2-axis. So we would be able to pick something along these lines right here. And yeah, the long axis, I'm thinking that would look like kind of like with the thing up against it, but maybe with the in this axis right here, in this orientation with the screen like this and the channel behind it, that might be a good choice. And we would pick this against this axis, so we would look for bending, and we would try to find a Z that would match up for what the minimum with Z would be. So let's actually take a look at that. What that would be. Okay, so first off, let's pick an arbitrary length of how high this would be. Let's say that this has to be 6 feet off of the ground. So that the distance that we're going to talk about here would be 16 feet right here. So the sum of the moments about this equals 0. So putting this into here, we would say, well, here's the reaction moment. Maybe I'll call it the reaction moment here, MR. And then this is going to be minus the drag of 17,020. And the moment arm is now going to be 16, but we want to get it into inch pounds. So we're going to find that reaction moment right there. And we're going to take it 17,020 times 16 times 12, and we get quite a bit, 3.268 e to the 6 inch pounds, right? And let's say that our yield strength is 36 KSI, right? 36,000 PSI. That's a steel called A36 steel, right? And we'll take a safety factor of 2. That's just, I don't know, we're just picking this out of the air. So what we're really saying is we're going to have a limiting stress of, or the allowable stress is going to be 18 KSI right up here. So we're going to be able to find Z by taking the moment, multiplying it by the safety factor, and dividing it by the strength. And so we get our 3.268 e to the 6. And let's make sure we get these units right. So let's move on there. And that's going to be times 2. And then that's going to be divided by our strength, which is going to be 36,000 pounds per square inch. And the pounds are going to cancel out. And what we're going to get for our Z is going to be in inches cubed, which is typical of a section modulus. So if we're going to multiply that by 2 and divide by 36,000, and we're going to need to have 181.6 inch cubes. So let's see if that's even possible, and it doesn't look like it is. Not from these, from these right here. So we're going to be taking our Z, our section modulus right here, and we see that we don't get up to that high. Even with, well, that's actually not too big. I guess maybe it is. Actually, that's pretty big. That's a 12, that's a foot wide thing right here. Oh, by the way, we should actually divide this by 2. All right, so maybe not because of the safety factor, but because there's going to be 2 of these right here. So let's say that this is 2Z. So our single Z is going to be divided by 2. That helps us out a little bit. And maybe 2 of these isn't enough. So maybe that's the solution between there, because we end up with 90.77 inches cubed. Maybe we can look this up for another let's see, where do I have that up here? go up to my Blackboard. Up in Blackboard, and my courses, and under Elements Mechanical Design, and I think, yeah, underneath my first homework problem of the semester, I have the students. Yeah, okay, so we go to this website right here. I guess I have to, it won't let me click on it. How come it won't let me click on this? There you go. Let's see if I can copy it and paste it in there. So, all right, yeah, so we got shapes. And we were looking for channels, so we didn't find any that we loved. Let's see, we could find a big, deep channel. Something here is an 18-inch deep one. And we got ZX is not going to be big enough here. Let's see. Looking for a pretty big one. How about you? No, here's a 75 right there. It's got a 75. It's 18 inches deep. Yeah, so you would probably want to use multiple ones because we're not finding any that are like 90.77. But that would be the design method that you would approach for something like this, to try to pick out what the material, the cross section that you would need into here. Yeah. So I picked out a pretty difficult problem. Let's see, that guy right there. He's still only 53.8. So I think the solution then would be to divide to have 4 of these legs instead of having just 2 for this wind resistance of 50 miles per hour to try to avoid it. So anyway, I thought that was kind of an interesting problem because we could combine some stuff that we've learned from fluids with some stuff from mechanics and materials and or machine design class. So that's it for this, and we'll do some more examples. So I think this is video 4 for class 17.